I've always been interested in math as far as I can remember, and actually farther back than I can remember. The first time I can remember my own interest is when in first grade our teacher asked all of us what we wanted to be. And everyone went around, and I was very proud that I actually managed to say mathematician. But I think she didn't expect that, or it was far from what she thought a 5-year-old should say. She said, "Oh, you wanted to be a magician." And I thought, well, that wasn't quite what I meant. But what I later realized is what I wanted to show people is the magic of math. So maybe she wasn't so far wrong after all. And so at least since I was 5 or 6, I remember math as my home base. Whenever I felt things were just a bit crazy, I remembered, the peace and quiet of a math problem. The world was your own. The pieces in it were limited. There weren't too many crazy things that could happen. And you could just chase your intuitions and ideas wherever you wanted to take them. So I always found great happiness in learning math and doing math problems. And then what happened in school was I was always just at least somewhat ahead of the curriculum in the school. So, for example, in first grade, I already knew how to add and subtract. And so I basically didn't spend any time doing what they were teaching us. The teacher said, here, you can do something else. So I then learned other stuff while everyone else was being basically brain damaged by the regular teaching method. And so I was spared that just by being a bit ahead. And so now in second grade, and in third grade, I was farther ahead because I hadn't been subjected to the usual teaching system. And so then I got to do other stuff. And while everyone else was forced to memorize multiplication tables, I got to learn about division and square roots. And I went farther and farther. So just from the happenstance of being curious about math early and then being a bit ahead, I always was spared the curse of our usual math teaching. So I really love math and still do. And so I always wanted to use math in some way. And then as I got towards high school, I got very interested in programming, which now I realize, that's just a species of math. And so it wasn't that different. But then I thought, it's different because math is on paper and programming you use these machines. But really, computers are mathematical systems. We made them that way. So you're actually doing math, but a slightly different kind or a way of implementing it. So that's what I wanted to do. Then in high school, I got selected to be part of the U.S. Physics Olympiad team. So there was 20 of us from around the country who were training to represent the United States in the rest of the world. So I didn't end up being one of the 5 people who went overseas, but I learned so much physics in that few weeks in the summer. And my teacher there, actually now Arthur Eisencraft, who is a renowned physics teacher in the country, he's now a professor of science education nearby at UMass Boston, and it's nice to still be in touch with my old teachers. But I then decided, in college, what I'm going to do is study physics. And so I did that, but before I'd done that, I'd always been interested in, for computer programming, how to make computers be smarter. So the particular way of being smarter was to play games better. And so I had written with a graduate student at Carnegie Mellon a World Championship Othello program. And so it played really good Othello, far better than I could barely knew the rules, but I knew them well enough to program it. But then the computer did really, really well. And so that was fascinating to me, and it was fascinating to me to see how the computer would learn. So we figured out a way of having the computer learn from its own mistakes, which is also what we'd like humans to do. We thought, humans learn from their own mistake. Let's see if we can teach a computer to do that. So I had that thread going, as well as the traditional mathematical thread in physics. And so in college, I did both. And then in graduate school, I just started out studying neuroscience because my old love for learning and first it was teaching computers, but then I was wondering, how do humans learn and how is knowledge represented? So I was a graduate student in neuroscience. But then my old bug bit me of physics, and I decided to return back to physics, which meant I lost my fellowship that I had for graduate school. So my advisor had money, to pay my tuition. So in the sciences, you don't pay your own tuition. It's either the research group you're working on or the fellowship has your back covered, so to say. So he was ready to do that, but I thought, well, I don't want to cost him so much money, so let me be a teaching assistant. I'd heard of this course called Order of Magnitude Physics, which everybody said, was the best course they ever took at Caltech. So I said, oh, well, I should take it. And I thought, oh, no, better than that, I should be a teaching assistant. I should help teach it. Then I'd learn even more. So I did that, and at the same time, I was studying for my qualifying exams in physics for the PhD qualifier requirement. And so in those 3 months of being a teaching assistant and trying to stay basically 1 week ahead of the students and studying for my qualifying exams, I learned more physics than I had in my entire 4 years of my undergraduate degree. So then I thought, physics teaching and learning are really broken. It could be much, much better. And then I only later realized, oh yeah, I've had this interest in learning for a long time, ever since I was trying to teach computers to play Othello and much better. And I always had this interest in math and physics. So I guess it was inevitable that I'd be interested in the teaching of math and physics and engineering and how to improve them. But that's how I always loved math and physics and wanted to show that to other people. And part of the way of showing that is improving the teaching so that you see the beauty in it and how it helps explain how our world is put together and how we may put it together in different ways and hopefully better ways. Well, with the teaching of math and science and engineering, I see so much that could be improved and made better. And in fact, that's just the very polite me speaking. The more honest me says, I am just outraged by how terrible it is and how people's love that they often have from young gets crushed by how we teach it. For example, we teach multiplication just as memorization. 6 times 9 is 54. And then 9 times 6 is 54. And then we memorize the commutative law that 6 times 9 is the same as 9 times 6. But students don't learn it as the meaning of multiplication. They just learn it as pieces of linguistic symbols. So a string of sounds, 6 times 9 is 54. And it could be anything. And there are all kinds of experiments now that show that the way people mostly learn, they haven't understood what we were hoping they would. They've learned it at a much more surface level and a much more symbol manipulation level or parrot learning. So a famous example of that was a study which asked students about pitchers of water. So you have a pitcher of water here that's 40 degrees and a pitcher of water here that's 120 degrees. So that's quite hot, and that's fairly cold, a bit above freezing. And then you mix the two pitchers together. What's the temperature of the water? And what do students say is they say, oh, do they mix it together and think about what would happen? No, they say, oh, that would be 160 degrees. So they just realize, okay, when you're adding things together, you add. I said that's surface level. So we have two numbers, we have 40 and we have 120. And so we add them together because it's this type of problem. It's an addition problem. So there's no connection to the world. There's no meaning in what they were doing. So it's just meaningless symbol manipulation. So of course, after years and years of it, people start to resent it, start to hate it. And as soon as they can be free, they quit. And they stop doing those subjects. So we wonder, well, why do so few students want to study math and science? Well, there's your answer. Because it doesn't seem to have anything to do with reality. So what I would like to do in my teaching and how I'd like our teaching to improve is I'd like it to connect to reality. And so that you build deep structures of knowledge that help you see how the world is put together. And that it's not a separate compartment of your mind called school, which is separate from the world. And you do school manipulations here and then you go out and do things in the world. No, these two are actually one and the same. And what you learn in school and in college are ways of understanding and changing the world. And so the first way to improve that is to change our focus on our teaching. Right now we focus almost entirely on content. You have to learn this one topic, then this next topic, then this next topic, then this next topic. and we transmit one topic after the other. But we don't think, well, how are these ideas stitched together, and how could students stitch these ideas together such that they stay in their minds for the long term? So what I eventually realized is that the topics are important, nice and important, but they're not the fundamental thing we're trying to teach. We're trying to teach ways of thinking that stitch and cut across all the topics. Now, of course, you have to have actual content that you're teaching, otherwise you're just talking about air. But you need ways of thinking, otherwise each topic is this isolated piece of knowledge which soon gets blown away by the winds of new knowledge and information that stream through us. So how do you connect things together? Well, first you have to find out what are the ways of thinking that are really valuable and generally valuable. And so that's what I ended up spending a lot of time, many years, working on. And so my book, Street Fighting Mathematics, was an attempt to do that for mathematical problem solving. So there are 6 ways of thinking and modes of reasoning in there that we can use for applying math to problems across the world of science and engineering. And then my next book, which is just about published in November, The Art of Insight in Science and Engineering, tries to do the same for science and engineering, developing modes of reasoning, ways of thinking that help us master the complexity of the world around us. And so both of these books, they're freely available to everyone. The one that's already published is already out there, Street Fighting Mathematics, and the next one, as soon as it's published, will be freely available to everyone so that this knowledge can be widely used and people don't have any barriers to accessing it and incorporating into their way of thinking. So what are these ways of thinking? So in The Art of Insight in Science and Engineering, I found that you could divide the ways of thinking into 2 broad groups, because the whole goal is to master the complexity of the world. Because that's what happens and that's what we'd like students to do, and what they usually can't. They come to a new problem and say, oh my God, I've never learned that particular problem. That seems so impossible. How do I even get started? It's as if they're confronted by this giant overgrown jungle of mess, and they need a few machetes so they can hack their way and start making a path and clear a path. So the first thing you do with complexity is you have to organize it. So you, for example, your desk. If it's just this pile of papers with no rhyme or reason to it, you can never find anything and you can never do anything, and you spend all your time just chasing your tail, looking for what you want. So you organize your papers into piles. You, for example, clean up one part of your desk, then the next part of your desk, or if it's your kitchen, that's what I try to do, one end of the kitchen to the next end of the kitchen, not the entire thing at once, which feels too overwhelming. So there are 2 ways of thinking for organizing complexity are divide and conquer, split a big problem into small problems, so do this piece, then this piece, then this piece, then that piece, or making abstractions, making groups. Okay, these are all my papers that deal with teaching science. These are all my papers that I need to read in the next day. These are all my papers that deal with teaching engineering. So we now have higher level ways of looking at what was once a big mess. Or for a kitchen, okay, here are my spoons, here are my forks, here are my knives. We don't put them all in one big jumble in a drawer. And in fact, we even have drawers, as the purpose being to make abstractions. So these form the first group of tools, organizing complexity. Or if organizing is not enough, you have to discard complexity. So that's the other choice, the other route you can take. And there's 2 ways to discard the complexity. You can either throw away complexity that isn't really there. It was just on the surface, kind of like barnacles encrusted on a rock, and you can scrub it away and you no loss to yourself or to the information in the problem. Or you can throw away information. And so an example of throwing away spurious complexity, not really there, is using symmetry. So you look at a problem from the right way, in the right orientation, the right point of view, and all of a sudden things are simple. You haven't changed the problem, you've just looked at it in a different way. And now it seems like, oh, how could I not have known that? But you've thrown away some complexity when you do that. So an example of using symmetry is, Suppose you have to add 1, 2, and 3. Now, that you can just do in your head, and it's 6. But I'll show you a symmetry way of doing that, which is probably what Gauss, the mathematician, did when he was 3 years old, and his teacher told the whole class to add the numbers from 1 to 100. 1 plus 2 plus 3, all the way up to 100, which would take a long time if you tried to do it by hand. But he had a symmetry way. So you say, okay, 1 plus 2 plus 3, well, that's the same as 3 plus 2 plus 1. So let me just take 1, 2, and 3, and flip 3, 2, and 1, and put them underneath. Then you have 1 and 3, that's 4. 2 and 2, that's 4. And 1 and 3 and 1, that's 4. So now, if we combine those two ways of doing 1, 2, and 3, we just get a bunch of 4s. And there are 3 of them. So that's 12. Divide by 2, you have 6. So we use symmetry, that this problem is the same when you turn it around. And then you've got rid of the complexity of it, that all the numbers are different. Now, all the numbers become the same just by this one symmetry trick. But, as Polya said, method is a trick I use twice. So once you use something like that twice, you realize, oh, there's a method there. And you give it a name. You make an abstraction. You collect all those uses together like you do for a folder of all your papers on one topic. So that's an example of using symmetry and getting rid of complexity, but no loss of information. Example of getting rid of information, but actually throwing away information, getting rid of complexity, is rounding numbers. So when I go to the grocery store, I always have a game with my daughters. We have everything in the cart, and then what we have to do is estimate how much the bill is going to be before it gets totaled up, or before we see it even being totaled up. Now, the hard way of doing that, and if you want exact answers, you have to look at what the price of every single thing is and add it all up. Now, computers are great at that, which is why the cash register was invented, and it does that for us. But if you want to get a feel for the numbers, you have to throw away the complexity. So now, my one daughter, who's 4, she always says it's $8, no matter how much. And I say, okay, that would be great, but unfortunately that's not right. But that's the number she understands. But my older daughter and I, we have more of a discussion about it. And the way I usually do it is I look at the shopping cart and I say, well, roughly how many items are there? Okay, about 80 items, and about how much is each thing, just as I was picking it off the shelf. Okay, maybe about $3 or $4. So it's going to be something like $300 for the bill. And so I've thrown away a whole bunch of information. Probably no item was exactly $3 or $4, and there's probably not exactly 80 items in the cart. But it's rough. You round things, you throw away complexity, but then you get some sense of what things should be in the world. And you can apply this principle to all kinds of calculations in the world and ways of understanding the world to reduce the complexity such that we can fit it in our minds, so that we, people, can master the complexity of the world and not just say, well, yeah, let my computer do that for me. So these, in sum, made 9 modes of reasoning and ways of thinking. 2 for organizing complexity, 3 for throwing away complexity with no loss of information, and 4 for throwing away complexity with loss of information. And so these ways of thinking, 9 together, cut across science and engineering. And what I did is I realized finally, this came to me very late in life after working on this book and way of teaching for maybe 15 years. Then I saw, oh, really, the ways of reasoning are more important than the individual pieces of content which you may not use again, because the ways of reasoning are more general and more transferable to students later in life, whatever they may do. Now, as I was saying before, you need the content, or the ways of reasoning are just air. So they're taught in some context of some actual problem. But the ways of reasoning, these 9 ways of reasoning, are what I want students and all readers to take away so that they can simplify the large, complicated, wonderful world that we live in and feel like they have some mastery over it and some connection to it. So I'd like to show a couple examples of how ways of thinking or modes of reasoning can help understand the world, and show you that with 2 concrete objects. These objects are 2 wooden blocks. So they're the same, except for one thing, which is that this is 2 centimeters thick and this is 1 centimeter thick. But they're both 30 centimeters long, about 1 foot, and 5 centimeters, or about 2 inches wide. And they're made out of the same piece of pine. They were cut for me by the machine shop of the Cambridge University Physics Department. And I've used them ever since to demonstrate sound and material physics and ways of thinking about that without having to use lots of equations. So the problem is to figure out the relative notes of these two blocks. So here's the note that comes from the thin block. So can you hear that? So that was the thin block. Now I'm going to tap the thick block in exactly the same way, which was just holding it here and tapping it right in the middle. Do you think that'll have a higher pitch, lower pitch, or the same pitch as the note I made with the thin block? So when I ask groups of physics students or often physics professors and mechanical engineering professors and students to think about that, I usually give people a few minutes to argue back and forth about what they think will happen, and then we try it. And then before we try it, though, people make their arguments. So here are some of the arguments that come up. On the one hand, this block, the thick block, because it's thicker, has a longer distance for the sound waves to move. So it takes more time for the sound waves to go back and forth in this thick block than in the thin block. So the frequency of the note made here in the thick block should be lower. On the other hand, some people say, well, but the thick block is stiffer than the thin block. Because of that, maybe this should be higher frequency. Then other people say, well, yeah, that's true, but look at this length. This length is the same as this length. And so the sound's going to take the same time to go across this length. So the frequency should be the same. And other people say, yeah, and it's also made of the same wood, so the sound speed's the same. It should be the same. So take your guess what you think it'll be, and I'll give you 5 seconds to just make your gut intuition, and then we'll try it. Okay, so here is the thin block again, just to refresh our memory. Here is the thick block. Can you hear how it's quite a bit higher? From the thick block? So this is by far the minority guess. Usually no one guesses that it'll be thicker, maybe one person out of 20. And even then they're not sure and they're sort of apologetic for guessing something that most people don't think. But why might that be? Well, one of the ways of thinking about materials is as springs, as just a big collection of springs. So this block is just a whole bunch of springs connecting a whole bunch of balls. And those balls are wood atoms. Now, wood isn't really an element, so there's no such thing as an atom of wood, but just pretend. That's part of throwing away information. So here's a wood atom, another wood atom, another wood atom. They're all connected by springs. And when you bend this block, which is what happens when you hit it, it gets bent, you're bending all the you're stretching all the springs, and you're putting a whole bunch of energy into those springs. And because this block is thicker, the springs here at the top compared to the top of this block get stretched far more, twice as much. So they have much more energy in them, and there are twice as many springs. So this block takes so much more energy to bend, so it's much, much, much stiffer. So the spring model, when you work out all the factors of 2, shows you that this block is much stiffer than this one, and far stiffer by a factor of 8, it turns out, than this one, which is far more than its weight. It's only a factor of 2 heavier, so that slows it down, but the factor of 8 in stiffness speeds it up by so much that this has a much higher frequency, almost a factor of 2. So that spring model, that was the thin block, the spring model is an approximation. It's a model. It's a way of throwing away information about the world, because it's not exactly a spring. It doesn't behave just like a spring, but it's close enough. And it's that willingness to use approximate ways of reasoning to throw away information that overwhelms us that allows us to make simple models that help us understand the world. So that's one example of ways of thinking and how they fit into a problem and a way of looking at the world. Here's another. which is these two cones. So these two cones, they're also cut out from the same sheet of paper, except this one has twice the radius as this one, so it has 4 times the area, the paper that it was made of. And the way they were made is you cut a circle out of the paper and then cut 1/4 of the circle out and throw it away, and then just tape it together. And here's the tape line, so there's your cone. Now the question is, when I drop these cones, which I'll do when I'm standing on the chair in just a second, when I drop them, how fast will they fall relative to each other? So here are the two cones, which I'll drop in just a second, and you'll see which one gets there first, or are they about the same. So the 3 choices are that this big cone goes about twice as fast, they're about the same, or that the small cone goes about twice as fast. Now, why might the big cone go twice as fast? Well, because it's heavier, so it pushes through the air faster. Why might the small cone go faster? Oh, because it's smaller, so it doesn't have so much air to fight through. Or maybe they're the same because those two effects balance. Not clear which one is right, so let's try it. 1, 2, 3. So they hit almost exactly at the same time. So those two effects almost exactly cancel out. Here you can see it again. Almost exactly the same time. And what that tells us is that the two effects exactly balance and cancel each other out. So on the one hand, the big cone has more air resistance because it's bigger. On the other hand, it has more drive because it's heavier. But because those two effects canceled out, and it didn't matter whether it was big or small, they landed at the same time, what we know is that air resistance is proportional to the area of the cone. And then when you add one more way of thinking, which is part of the whole collection of ways of thinking for throwing away information without losing any information, throwing away complexity without losing any information, that method of reasoning within this group is called dimensional analysis, which says that you can't add apples to oranges. So you can't add feet to seconds or meters to square meters. So with that one idea, plus the result of this experiment, that they land at roughly the same time, you can work out the way air resistance depends on speeds, areas, and density of air. You can work out the gas mileage of a 747, of a car. You can work out how much peanut butter a bicyclist needs to bicycle 1,000 miles. So you can work out the fuel efficiency of a bicyclist. And you can do that all from the simple paper experiment. And you can check the conclusion with this one follow-up experiment. So the follow-up experiment is to stack 4 little cones together. So here's 1, 2, 3, 4. So now I've made a heavy small cone, 4 times heavier than this one. And now the conclusion of the other experiment, after you use dimensional analysis, is that the air resistance is proportional to the square of the velocity. So if you double the velocity, you'll quadruple the air resistance. So how should these two fall, this group of 4 versus the 1? Well, the group of 4, which is heavier, is going to fall faster. But how much faster? Well, it has 4 times the weight. So as it's falling, it'll have 4 times the air resistance force. Now, how's it going to get that? Well, it can't be because it's bigger, because it's the same size as this one. It can't be because the air density is different, because the air density is the same for both of them. So it has to be because it's going to fall faster. How much faster? Well, it turns out it should be a factor of 2 to compensate for the factor of 4 in air resistance. So let's check that. So we could actually drop them both at the same time and measure the speeds and say, oh yeah, that looks like about a factor of 2. But instead, what I can do is I can drop them with this one at half the height of this one. So it looks about half the height. And then I drop them at the same time, and hopefully they land together. Exactly at the same time, with almost exactly half the height for this single cone. So that's our confirmation that the other experiment didn't lead to nonsense, and gives us more confidence to use it to understand the physics of fuel consumption in the world around us. The purpose of these ways of thinking in these demonstrations is to show you a different way of thinking about math, science, and engineering. That it's not just a series of formulas, one after the other, which need to be memorized and then reproduced on a test, and then numbers plugged into these pieces to get some other numbers. But it's a way of understanding and making sense of the world. It's a way of also getting away from what too often happens from just teaching through formulas is we teach people rigor is important, rigor is important, rigor is important, and the importance of rigor. But then the result is people get rigor mortis. They get so stiff, they're so afraid that if they don't have the formula, they can't do anything, that they sit there paralyzed. And there's no joy in that. There's no enjoyment in looking at the world and understanding it with that kind of paralysis. So these ways of thinking, and these are ways of unblocking, unsticking, and freeing your vision and your sight, your ears and your whole senses to understand and see the connection in the world around you. And the demonstrations are to show that these apply to real objects, that the world is actually in some way built of these ways of thinking, and that it's a beautiful way of looking at the world, and that science, math, and engineering have a lot to say to us, and that everyone should keep studying those for many years and make our world better.